what was curl? Curl was um, it was a rate. So if you had a vector field, if we have a vector field, um, PQR is what we want. So we have some vector field, right? And we said that if this was a gradient field, then it would be the rate of change of some potential function, right? It would be the rate of change, like the derivative of some potential function, if it was a gradient field. But then we said whether or not it's a gradient field, it itself is its own function, and we could analyze its rate of change. And so we said the rate of change, there were two types of rate of change of a vector field. And the first one we looked at was curl. So curl was like rotational rate of change, like how much tendency of rotation. And so we saw that for an element, kind of the horizontal components of the vectors in the field above and below the element caused rotation, and then the vertical elements to the right and left kind of caused rotation. So then in 3 dimensions, we had kind of 3 components of that, all causing rotation, and we came up with this formula here from the cross product. So the cross product of the gradient operator, which is the partial derivative operators, and our vector field, PQR. And if you follow the cross product algorithm, you get the new vector field, which is the curl. And this is a vector function that gives us tendency of rotation at every point. Pointwise, it's a pointwise function. And then here's the formula for it. So you can, if you're finding the curl of a vector field, you can either just execute the cross product algorithm, which is what I do every time, or you can apply the formula. But then you'd have to look it up or memorize it. And so I just go ahead and do the cross product algorithm every time. But then this is what you get. And so this is the value of the curl given your vector function PQR. It's these differences of these partial derivatives that form the components of the curl. Okay? And then remember that we said that if the curl is 0, so if all of these are 0, then there's 0 rotational rate of change, and that is called an irrotational field. Meaning there's, at every point in the field, there's no tendency of rotation. Okay, and then we said, okay, look at that. So that if qx minus py is 0, that means qx equals py. And what was that? What did we have if qx equaled py?
Conservative field?
Yeah, conservative field, gradient field. So irrotational fields are conservative because you get that these partial derivatives are equal. So that means in an R3 field, if you wanted to check an R3 field to see if it was conservative, you would have to check qx equals py, but you would also have to check that pz equals rx, and you would have to check that ry equals qz. So if you checked all 3 of those, and all 3 of those were 0, that would be your check for conservative, because that would be an irrotational field, and then you'd have a conservative field. So this is like for an this is like the Clairaut's theorem check for an R3 field would be you'd have to check you'd have to compare 3 different pairs of partial derivatives to make sure that they were all equal. And then you can conclude it's conservative. Or you can do the old method, which is just, if you're trying to see if this is a conservative field, just try to find the potential function, right? You just like start going through the algorithm of trying to figure out, is there a potential function that has these 3 as partial derivatives? Okay. If it does, then it's a conservative field. If it's impossible for a potential function, it's possible for these to be partial derivatives of some potential function, then it's not a gradient field. So kind of two options for checking if a three-dimensional field is conservative or not. See if it's irrotational by doing all these, it's not like three Clairaut's theorem equations to check, or just try to find the potential function. Okay, so questions on, that's kind of an overview of curl. Questions on that? Okay, so then we said there are two types of rate of change. The one is curl, rotational rate of change. So let's look at the other. The other type of rate of change is in fact easier. The curl is the harder one. So the other type of rate of change of a vector field is called divergence. Divergence is where curl is like the rotational rate of change. Divergence is the expansion rate of change. It's the expansion rate of change. So again, we're going to take our small element, and we're going to look at the vectors around it, and we're going to isolate the components of the vectors. We're going to get those vectors. And now we're going to ask, which of these components, so let me I'm going to redraw all the, man, oh man, technology. Okay, I'm going to redraw these components of these four vectors kind of right at the point. This, right at the point on the, so all I'm doing here is redrawing components of FT, FB, FR, and FL. Okay, so looking at the top and bottom FB and FT, now which of the vectors, either the P horizontal or Q vertical, would contribute to like pulling on this expansion or contraction? Would it be the horizontal vectors or the vertical vectors?
Vertical vectors.
The vertical vectors, right? The vertical vectors would be like, wouldn't be turning it, it'd be like kind of pulling on it, stretching it, or smushing it together. Okay, so we just care about then, and that would be in the y direction. So for a change in y, all we care about is the y components of the vectors, or the q vectors. So we don't care about the horizontal. And then likewise, in the horizontal direction, the horizontal vectors are going to be what's contributing to like pushing together or stretching apart.
Horizontal?
Yeah. So in the horizontal direction, for a change in x, what is it that determines the change in p? What is it that determines the change in p for a change in x? What's the key quantity there? So given a change in x, how do we determine the change in, say it would be these vectors here, the change in the x component of these vectors for a change in x? What would
we add the x components together?
No, so this is a familiar, right? This should be a really familiar equation that we've seen this semester with a really key concept right there.
Yeah, would it be the force vectors? Like f of
The two?
So given a change in independence, what determines the corresponding change in dependence?
the partial derivative of p with respect to x.
Thank you, partial derivative, right? The partial derivative is what's governing changes in in this case, changes in these vectors for a change in x. So it's the partial of p with respect to x. And then likewise, for a change in y, we're looking at the change in q. So that's
and then the partial derivative of q with respect,
yeah, that's right. The partial, yeah, exactly. Partial of q with respect to y. So the reason that divergence is easier is because, look, for a change in x, we only care about the x component of the vectors. It's a match, right? P is the x component of the vector, and P, the change in P is important for a change in x, horizontal. And for a change in y, we look at the change in Q, which is the y component. So now our independent variable and the part of the dependent variable that we're looking at are the same variable. So that's what makes divergence so much easier. Okay, and so if dp is positive, so I need to draw a positive, I need to make this bigger here. So if from over a dx, if your dp is positive, meaning this vector is bigger, then that would be a positive rate of change, and would that indicate expansion or contraction?
Expansion.
Yeah, expansion, right? So it's like things are opening up, things are getting bigger, things are going faster, right? As x increases. And likewise, if for a positive change in y, if you get a positive change in q, that's going to indicate expansion. So positive divergence is indicating expansion at that point. It's a point-wise phenomenon. Negative divergence is indicating kind of compression, or things closing in on the point. Okay. So the total rate. So this in R2, the total rate of expansion would just be the sum of the two partial derivatives. There's no minus signs to worry about, and there's just all it is this contribution to expansion plus this contribution to expansion. In R3, then you'd also have the partial of r with respect to z. So that's what I'm showing here. And so what's happening here is we are taking what? It's the partial with respect to x of p plus the partial with respect to y of q plus the partial with respect to z of r. Now remember that curl was the cross product of these. It was the cross product of the gradient operator and the vector field. So what about this? What does this look like?
The dot product?
Yeah, so it's like we're going to assign the partial with respect to x to the x component, the partial with respect to y to the y component, the partial with respect to z to the z component. So that's just the dot product. So we're just summing together the three partial derivatives, which could be expressed as the gradient operator dot the vector field, right? So then you do the partial of x with respect to p, the partial of q with respect to y, the partial of r with respect to z, and you add them all up, dot product. And so then, do we get a scalar function or a vector function then?
Scalar.
So this is a scalar function. Remember, the curl of f was a vector function. There was the strength of rotation, but then also direction of rotation. So remember what the direction of the curl vector was?
Orthogonal.
Orthogonal to
The plane.
the plane of rotation, right? So if this, say at this point right here, if our rotation is kind of maximum in this plane for the field, then the direction of the curl vector will be orthogonal to that plane, the plane of rotation. Okay, but divergence doesn't have direction. It's just an amount. It's just like how much expansion or how much crunching, right? So that's why we get a scalar function. It's just for every point. It's still pointwise. It's still different in different locations, but all it is a number that indicates if it's positive, how much expansion kind of tendency there is. If it's negative, how much compression there is. But that curl is a vector function. There has direction, right? Orthogonal to the plane of rotation. as well as strength of rotation. Okay, questions on divergence? Much easier. So student example of divergence, we'll use that same, we're going to use that same example we had last time that we did for curl. Let's do that. Second one. So this one. So here's this second example we saw last time. And so let's visually, first we're going to visually determine whether the divergence is positive, negative, or zero. And so the way you do that is, so you could pick a point here. And you look at the general motion around that point. So which way is the general motion at that point? The general motion is up and to the left. And then, so then you look at vectors behind and in front. And you say, if our general motion is this way, then if we have a smaller vector behind and a larger vector in front, is that a tendency of expansion or is that a tendency of compression?
Expansion.
Expansion, right? So the fact that things are opening up, they're going faster, it's widening, right? So this indicates expansion, so divergence is what?
Positive.
Right, so the divergence here is positive. What about in quadrant 2? Look at the general direction of flow, and then look at vectors behind and in front.
It'll be compressing.
Yeah, right. So now things are like slowing down, crunching together, right? Coming up from behind with greater magnitude than going out in front. So divergence here in quadrant 2?
Negative.
Negative. All right, same thing here. Quadrant 3, what do you say divergence is?
Positive.
Positive, right? Direction of flow. And things are increasing, expanding, widening. And in 4?
Compression.
Compression, negative. Okay, so here, so like we said, these functions are point-wise phenomenon. So you move to a different point, you get a different divergence, you get a different curl, right? Every point in the plane has a curl and a divergence. So these are point-wise functions. And so here we're seeing how the divergence can change as you move around, right? Positive over here, negative, positive, negative. So if we look at this actual function and find the divergence, it should agree with our visual estimates here. So the actual function for this is this is negative y x to the minus 2, x to the minus 1, and 0. So that's what this vector field is. So we're going to find the divergence. And to find the divergence, what we do the dot product of the gradient operator with the components of the vector function, which is simply partial with respect to x of the x component, partial with respect to y of the y component, partial with respect to z of the z component, and add them up. So what's the partial with respect to x of the x component?
Positive 2x y x to the power negative 3.
Right. That's a 2, not that's a 2. There we go. 2y over x cubed. All right, what's the partial of x to the minus 1 with respect to y?
0.
0.
Partial of 0? So here's my
0.
function, 2y over x cubed. So this should agree and give us the same things that we did with our visual inspection. So in the first quadrant, what is 2y over x cubed? Is that positive, negative, or 0?
Positive.
Because?
It's expanding.
No. Now we're doing it algebraically, right? Yeah.
All values are positive both on the numerator and denominator.
Yeah, so in the first quadrant, we know that x is what? X is positive, y is positive, and so if x is positive and y is positive, we'll get a positive over a positive, which is
Positive.
positive. Let's just do that. Positive over positive equals positive. All right, quadrant 2. X is and y is what?
X is negative, Y is positive.
So it'll be negative.
Right, because you'll have a what? Positive divided by a negative, and that'll equal negative. And that agrees with what we said. Divergence was negative. Here, x and y are less than 0, so you have a negative over a negative.
Positive.
Positive. So this value will be positive. That's what we said by looking at the vector field. Finally, x greater than 0, y is less than 0. You'll have a negative over a positive. Negative over positive in the formula will give negative. That's what the divergence is. Okay, so does this make sense? This thing with divergence, right? It's a pointwise function giving the rate of change, expansive rate of change at every point, and that's just a number at every, it's just a value, not a vector. So if the divergence is 0, if you work through all the partial derivatives, add them together, and you get 0, then the field is called incompressible. There's no tendency anywhere in the field for expansion or compression. Now that is irregardless of whether it's a conservative field or not, right? So our irrotational field, the curl being 0, that gives us a gradient field or a conservative field. And we found out that we did the curl formula, we did the algorithm, and we got the curl to be 0. So this is a gradient field. But notice it's not incompressible. So you don't have this relationship between incompressible fields and gradient fields the way you do irrotational fields and gradient fields, right? So you can have gradient fields or non-gradient fields that are compressible or not compressible. Here's an example of a gradient field that is not incompressible, right? It has a non-zero divergence. All right, questions on divergence?
Question?
Yeah, question?
So, in regards to being incompressible, is there anything other means we can attach with it, or is it just that it's incompressible, that there is no change in or expansion or shrinking?
Right. So yeah. So as if you put something in this as a fluid field and you put something in it, there would be no there'd be no tendency. There'd be movements through the field, but there'd be no tendency anywhere towards expansion or compression anywhere in the field. Beyond that, I'd have to do some research.
Okay, thank you.
Okay, you're welcome. All right, so given a vector field, two kinds of rate of change. There's rotational rate of change, that's curl. That's a pointwise vector function. And then there is the other type of rate of change, which is the divergence. And that is the rate of change that gives tendency towards expansion or compression. And that's also a pointwise function, but that's a pointwise real valued function, or a scalar function. You get real values from that. No direction involved in divergence. Okay? So we're going to change gears now. And we're going to talk about what's called, we're going to talk about parameterizing surfaces. So far, we parameterized curves. What kind of function do we use to parameterize a curve? I've been doing it a lot of the semester.
Parametric.
Right, a vector function, right? A vector function is what parameterizes a curve. So remember, so we've got some curve C. We're doing a line integral, or we're tracing along C. And so if it's a curve, how many parameters do we need?
One.
Just one. Why? What is it about a curve that kind of associates or corresponds with the fact that we only need one parameter, one kind of degree of freedom, so to speak? What is it about a curve that it makes sense that you only need one parameter? It's because in a string of points, you can only go one way, either forward or backwards, right? So at this point, you can either go forward or backwards. That's only one direction, right? There's only one direction you can go at any given point. And so t is enough. T is enough to define all points on a curve, because a curve is, even though it could be in space, it's still like a one-dimensional thing. Make sense? All right, so therefore a surface then. What would we need for a surface? Could we do it with one parameter?
No.
Right? So on a point on a surface, how many kind of degrees of freedom do we have on a surface like this?
2.
Yeah, so given any points, you could think of like a tangent plane to that point, right? And a plane requires two variables to define points on a plane. So a parameterized surface is going to, they're like two-dimensional, even though they can be in R3 and bent and wavy, they're still two-dimensional surfaces if you look at just one point. So we're going to need two parameters. And so generically, we call those parameters u and v. Okay, so but then we're going to see that we're going to use different names. But generically, these parameterized surfaces are vector functions of two variables. All right, and so then it's going to be some function of u and v as the x component, some function of u and v for the y component, and some function of u and v for the z component. But again, it's just a way of defining every point on the surface, just like our vector functions were a way of defining every point on the curve. And that's by vectors in standard position. Right? Put these vectors in standard position, and then all of them will point at the points on the surface. But these components of these vectors that come out of this function, they're the same as points on the surface, just like parameterized curve. So let's look at how this works. All right, so surfaces, any surface that's given as z as a function of x and y are the easiest. Okay? Because we can just use x and y as the two parameters. And remember, the vectors coming out of this vector function are giving us points on the curve. So if our parameters are x and y, what are the x components of the, what are the x components?
X.
Just x. And what are the y components?
Y.
Just y. X and y are free to vary and be themselves. And then what would z be? Now we only get x and y to express x, y, and z.
So we would use the function as z?
Yeah, this is what z is, right there. That's what z is, right? Done. So if your function is a function of, if you have a surface that where you have z as a function of x and y, and that was a lot of them, right? A lot of our surfaces were like that. Then then it's so easy, right? You just make x, x, y, y, and then z is whatever the formula is for z in the function. Okay, what about this one? So can I apply the same thing? Do I have z as a function of x and y? I have the part of this plane inside the unit square. So some plane, this, and then we just want the part of that plane, say like this. I just want the part of the plane that's above the unit square, something like that. So, can I apply this technique for parameterizing? Can I write z as a function of x and y?
Yes.
If I can, then I can simply write the function as x is x, y is y, and what is z?
8 minus 5x plus 3y. That entire term divided by 2.
Yeah, just solve that for z. And that's my kind of my multivariable function when I solve for z, multivariable function of x and y. But now I want to restrict my domain. So I want x from 0 to 1, y also from 0 to 1. So when you take a piece of a function, when you carve out a piece of a function, though the part you're taking doesn't change the function itself. It just restricts what part of it you're taking. So if we had taken a circular, or like a circular piece of this function, that wouldn't have changed this at all. That would not have changed this function at all. It just would have changed which x and y we're considering. Okay, does it make sense? Oh, so let's do this one, top half of the cone. So the top half of the double cone. So which is the top half of the double cone? Z equals
Square root.
Yep, so it'd be positive square root, right? When you take the square root of both sides, you get positive and negative. That's the top and bottom of the cone. Positive z values are the upward opening cone. Negative z values below the xy plane, or the downward opening cone for negative z values. So we want the upper half, we want the positive square root. And then, so now we want below z equals 7. Now, it's not, you really can't say, z less than 7 because z isn't one of your independent variables. You got to do this in terms of x and y. So at z equals 7, what do we have at z equals 7? 49 equals x plus 1 squared plus y squared. So that's what? That's that circle at level 7. It's the circular cross-section of the cone. So if we come down and project that into the xy plane, so what points on this? So in the xy plane, that can define our x and y coordinates. And which x and y coordinates will get us the points on the surface below z equals 7, all these points? Well, won't it be the points inside the disk? Won't it be the xy coordinates inside that circle or that disk? Will give us all the points on the cone less than z equals 7. So how do we specify that? How do we specify all xy ordered pairs inside the circle with radius 49?
You just write down the equation of that circle that you wrote.
Yeah.
Less than 49.
Yeah, less than
to 49.
Less than 40. So if it says strictly below would mean we don't include radius 7.
Oh, okay.
So there it is. That's R, not F. That's R vector.
How do you know when to do like less than and when to do less than or equal then? Because for the previous example, it said like inside the unit square, but we did.
Oh, you're right. I should have done less than. Here.
Oh, okay.
Yeah, these should be all less than if I'm being technical about it. Yeah, that's true. Inside would be not including the square. Okay, questions on that. So that's the easiest type of surface to parameterize. When your surface was z as a function of x and y in the first place, then you just use x and y as your two variables, and then your formula for z as z. And again, this is what the vectors that you get are the ordered, they correspond to ordered triples on your surface. They're defining the points of the surface. It's just they're defining them as position vectors, right? Standard position vectors. Vectors at the origin pointing up at the points.
So for the coordinates that it's restrained within, for x, would it be from -8 to 6, and then for y, -7 to 7?
No, because that would be a square then. If you said that, that would be a square.
Oh, okay, I see.
You got to do that equation. You got to do
that-
equation with a radius and say less than the radius.
Yeah, that makes sense.
Yeah,
Thank you.
Sure. Okay, cylinders. What were cylinders? Cylinders, we defined a curve in two variables, and then we swept it in the direction of the third variable. So for instance, if I had z equals y squared, in R3, what is that? Is that a parabola in R3? It's not a parabola. What is it?
So
A parabolic cylinder.
Parabolic cylinder. It's a cylinder, right? X can be anything. So at any x value, we get that same parabola. All x values, we get that same cross-section parabola. And so it's like this trough that runs on the x-axis. So we can use one of our parameters. We got two parameters to write all points on this surface. We can use one of them to write the curve, and then the other one to be the sweeping variable, right? So that's like in this case, x would be one variable, and then we'd have one more parameter to define the curve z equals y squared. So how about this one? Y equals e to the minus x. What will I use for my two parameters?
X e to the e to the negative.
No, I'm not asking for the vector yet. I'm asking for what will I use for the two parameters. What?
X and Z.
Someone said x and z, right? So we're going to use one of our parameters to define that curve, and then the other parameter will be z. So z can run. So at every z value, we get this curve, right? Every z value, we get that curve. And we got one more. So we're going to use x or y. What's the better choice here for this?
Y
Is it y?
or X?
It'd be x, right? Because then you can just write y down, right? What is y then?
e to the negative x.
There you go. And then z. So this defines all points. What is this? Y, see the negative. It's like this. This. So that looks like this. And so this vector function will give us every point on that surface, right? X and e to the minus x gives us every point on the curve. And then you get for every z value, right? Up and down. And that gives every point on the surface. And then it says lies behind the yz plane and above z equals 2. So behind the yz plane would be x less than 0. Above z equals 2 would be z greater than 2. And those are our independent variables, so we're good on that. Questions on cylinders. So one variable to define the curve, the other variable to define the missing variable, where the in this case z, where we sweep the curve and get all the different that same curve over and over again for the third variable. Okay, next, circular surfaces. So remember when we had circular curves, ellipses and circles, what did we use for the parameter? No, what do we use for the parameter? What's the variable, the one variable that we have to get us all the points on an ellipse or a circle?
T.
What does that t represent? What quantity is that t?
Theta.
Uh-huh. Right, theta. Okay, so in the same thing with circular surfaces, we're going to use theta as one of them. And let's just do this first example and see what else we're going to need here. So if x is y squared plus z squared, that's the paraboloid opening in the positive x direction. And so yeah, so we can use theta to define these circular cross sections. And what will theta be involved in? X, y, or z?
X.
So is theta defining the x of these points on the surface? Right, theta would be like going around each of these circles, right?
Theta defines y and z.
Yeah, theta is defining the y and z coordinates around these circles, isn't it? So we could assign, say, cosine theta to y and sine theta to z. But that would be a circle of radius 1. Do all these circles have radius 1?
No.
No, they have varying radius. So that's the other variable we're going to use because the radius is varying. So besides theta, we want?
Like a radius r.
Yeah, r, right? So we want r. So then with a varying radius, then we have r cosine theta for y, r sin theta for z. Then how are we going to figure out what x is?
You would substitute the y and z variables into it, and then
Yeah, we got to have this paraboloid, right? So we've defined a y and z, but we got to make sure we have this paraboloid, which x is equal to the square root of y squared plus z squared. So this is going to determine what x is. X is going to be what? Y squared plus z squared.
So x is just r squared.
Exactly. So then you factor out r squared, and you get r squared times 1. X is just r squared. And if x goes from 0 to 25, that means r goes from what to what?
0 to 20. No, 0 to 5.
0 to 5. So there we got it. So we know our circle is going to be in y and z. So our cosine and sine are going to be in y and z. But this is a varying radius, so we need to account for that. That's our other variable. And then once we have that set, x has to be in this relationship, y squared plus z squared. And that gives that x is r squared. Okay, one more. Quick. Cylinder. It's a cylinder. X squared plus z squared equals 12. That looks like this, right? It's a cylinder down the y-axis. What are our two variables going to be? R and theta again? So getting all the points on a particular circle requires what?
Re.
What variable can get us all the points on a circle?
Theta.
Theta. Now, do we want r to be the other one?
Would we just have y be the other variable because the radius doesn't change?
Yeah, the radius is constant. We don't want to waste our one of our two precious variables on radius when it's just square root of 12 everywhere. Instead, it's a cylinder, right? So the other variable is going to be getting all the circles all along the cylinder. So it'll be
Just y.
y. You got it. Yeah. So then x and z square root of 12. So we're going to have radical 12 cosine theta for x and radical 12 sine theta for z. So that x squared plus z squared equals 12. And then y. And that will give us every point on that surface. So theta gives us every point around a circle. Y gives us all the circles. First octant means that y is greater than 0. So, and then what? Only this part here. So what angle measure is that? First octant. going to be from
Maybe
0,
0 to pi over 2.
0 to pi over 2, right? It's going to be that quarter circle starting from, so that is the x direction and z. So looking this way, counterclockwise from x up to z, would be 0 to pi over 2. And that gives us just the part of the cylinder in the first octant. Questions? Okay.